Right, thanks everyone for coming. I'm sure you're all ready to call it a day, but hopefully we'll have a little bit of fun today. This is more of a fun talk. It's just stuff that you don't normally talk about, which is old stuff, which I think is actually still quite new. I don't think it's necessarily just for old people. So I'm Scott. This also talk is really, what can we learn from the 1970s? Turns out there's a lot we can learn, and there's a lot of stuff we haven't even learned, even though it's 40 years ago, and there's some stuff from 40 years ago that we're still not doing. So I'm at F sharp for fun and profit, but I'm not going to be talking about F sharp very much in this talk. It's about other things. So this is the 1970s. This is a photo taken in the 1970s. As you can tell, it's a very long time ago. And in fact, I am quite old. I am so old that I was actually alive in the 1970s. And this is a photo of me down there. So, all right, so 40 years ago, a long time. I'm going to talk about 4 languages, or maybe 5 languages, actually definitely 5 languages. I'm first going to have a very quick history of programming languages, because that's always fun. I'm going to talk about hammers and toolkits, and we need to stop using so many hammers. And then I'll talk about the languages, which are SQL, Prolog, ML, and Smalltalk, and Language X. So let's start with a brief history of Smalltalk, brief history of programming languages. Right, a language that does not affect the way you think about programming is not worth knowing. This is one of my favorite quotes. And there's so many languages we learn, you know, they're useful like Java or something, but it's not going to explode your brain. So I'm going to give a galaxy brain seal of approval to languages that literally alter your brain chemistry. So, okay. In the 1950s, it was basically a dead time. I call it the pre-Cambrian era. There was not many life forms around. Pretty much everything was an assembly language, and each mainframe had its own assembly language. Fortran came along, and what a concept. You could actually have a portable language that would run on more than one mainframe. Wow, you didn't have to memorize the assembly code. So that's a galaxy brain, the first high-level language. Definitely changed the way people thought about programming languages. COBOL came along shortly afterwards, and COBOL is the first enterprise language, and we've been saddled with enterprise languages ever since. Lisp came along in 1959, and Lisp, of course, gets a galaxy brain because it's the perfect language, just because it's Lisp. Lisp has always been the perfect language, always will be the perfect language. Here's the problem, that Lisp never really took off. And there's a very interesting essay called Worse is Better by Richard Gabriel, which I highly recommend if you want to know why Lisp hasn't taken over the world and C has taken over the world. So in the 1960s, stuff started happening a bit more. There were a lot more computers around. IBM and the Seven Dwarfs, they call them, because it was IBM, and all the other ones were kind of smaller companies. Algol 60, the clue is in the name. This is really the foundation of all other modern imperative programming languages. Incredibly influential language. Basically, all modern languages are basically derivatives of this, or most imperative languages are derivatives of this. This is a great quote. This is 13 years after Algol 60. It was so far ahead of its time that it's also an improvement on its successors, let alone an improvement on its predecessors. I think it's a good quote. That's by Tony Hoare. So even in the 70s, people still weren't doing Algol very well. So BASIC is another one, 1964, that's a long time ago. And what a concept, a language that beginners can use. I mean, actually, they designed it for liberal arts students at Dartmouth College. Obviously, people who weren't even going to be programmers could even use it. That was how simple it was going to be. PL1, 1964, it was touted as the only language you'll ever need, right? We know how that turned out. How many people still use PL1, right? But yeah, it's one of those things. It's going to be the perfect language that solves all our problems. ISWIM, 1966. This is the most influential language that was never actually implemented. I like to think of it as like the Velvet Underground. You know, nobody ever read this paper, but the people who did read this paper went on to write other programming languages. So it's the parent of functional languages. It was the first language used indentation for scope. So if you used Python or Haskell or F sharp, the white space indentation of the offside rule comes from ISWIM. So super, super important. APL. This is the first write-only language. It's famous for that. But actually, it's not, people make jokes about APL, but in fact, the point was that mathematicians think in symbols. They don't think in terms of words. So why not have a language that is the same kind of symbols that mathematicians would use? So notation as an aid to thought, the idea is the notation reflects the way you think. So that's actually a very important concept. And Ken Iverson, who wrote APL, actually got a Turing Award for it. So APL gets a galaxy brain, because if you learn APL or a modern version like J or something, it will definitely change the way you think about programming. Simula 67, which came out in 1967. First language with classes, inheritance, and all the stuff that we used to. Now, nowadays, we would think this is very kind of run-of-the-mill, but at the time, there's quite a radical concept, a lot of this stuff. So Simula gets a galaxy brain. A lot of galaxy brain stuff going on, because this is the very first time that these things had happened. BCPL, infamous as the first language with curly braces. So I hate curly braces, and so I'm going to blame BCPL for that. It is the grandparent of C, and so C took a lot of bad habits from that. Poor people. Right, logo. Now, if you think having, English students learn programming is pretty advanced, how about having children learn programming? So Logo was a language designed for children. This is in those days, they were still using mainframes, right? So they're using mainframes and they're expecting children to program. So the idea is that programming actually changes the way you think, or it helps you interact with the world. And if the children learn to program, it would help them to be better human beings. That's not something true anymore. Algol 68, so another version of Algol. Very influential as well, very, very complex. Didn't really take off like Algol 60 did. So we come to the 1970s now. This is a decade where I think computers are becoming cheaper, a lot more programming languages were invented, and more importantly, a lot more programming paradigms were invented. This is where we see all the modern programming paradigms kind of come into fruition. So the first one is Forth, the first concatenative language. Very interesting. You get a galaxy brain if you use Forth. Again, it will change the way you think about programming. There's an interesting book called Thinking Forth, which I highly recommend, about how to write program. It's actually available for free. It's a PDF download. But it was the first book, as far as I know, that used the word factoring, as in refactoring. It's a way of thinking about breaking things into smaller pieces. Pascal, which is like Algol for the rest of us, really. It was kind of simpler and faster, still popular. C, of course, you've probably heard of that one, which is still going strong. Prolog. So Prolog is the first language, or the first major language, that introduced another new paradigm, which is logic programming. Again, if you learn how to use Prolog, it will really do some mind-expanding things to your skills, and we're actually going to talk about that later on. ML, which also introduced a new paradigm, which is functional programming. A lot of groundbreaking stuff going on, and we'll talk about that in a minute. SQL is another one. So SQL introduced a whole new paradigm of relational programming, and it came along with the first relational database, but the concept of actually programming interactive queries using a standard query language was very radical. So you galaxy brain for that. CLU, another important language with abstract data types, iterators, exceptions. Again, most modern languages owe a debt to CLU. The person who worked on that with her team was Barbara Liskov, and you've probably heard of the Liskov substitution principle. So that's where that comes from. Another one, which is Scheme, which is another version of Lisp for the rest of us who didn't like Common Lisp. Actually, Common Lisp didn't exist back then, but you know. Microsoft Basic. So what a concept. You can actually program your 16K microprocessor using Basic. Pretty radical. That you have a personal computer that actually sat on your desk. Quite incredible, really. And you can program it. Amazing. So Smalltalk, which went through various variants, 1972, but 1976 was a big one, and 1980 was a really big one. Amazingly important language. The first language with an interactive IDE. It had a virtual machine. It had garbage collection. We'll talk a little bit. Definitely many, many, many galaxy brains to Smalltalk. And I recommend anyone learning, you should learn Smalltalk even today, because again, it will change the way you think about programming. Smalltalk people like to call this real OO, as opposed to the sort of similar OO that we're used to with Java and C# and so on. What's also interesting about Smalltalk is the ex-practitioners are very, very influential. If you look at the Gang of Four patterns, that has Smalltalk as this example. The XP community, the Agile people, the refactoring people, these are all people who came from Smalltalk. So Smalltalk was very, very influential in the way of thinking about programming. Module 2, I like to call this the Golang of the 1970s. It was meant to be small and very fast, and it had concurrency built in, and all the kinds of things that people say about Go today. You could probably say that about Module 2. So, very, very nice language. And finally, we've got language X, a mysterious language. I'm not going to tell you what it is. It scrapes into the decade. It came out in November 79, I think, and it's the grandparent of the most popular programming language ever. So that's a clue. And I think it deserves a galaxy brain because it changed the way people think about programming as well. So if we look at the important programming paradigms, we've got the imperative procedural, which came from ALGOL. We've got object-oriented, which came from Similar and Smalltalk. We have functional programming, which comes from ML. We have symbolic programming from the various Lisps. We have logic programming from Smalltalk. We have concatenative programming from Forth. These concepts all originated in the 1970s, 40 years ago. Every single major programming paradigm that we're familiar with is 40 years old, at least. So there you go. It's kind of shocking, really. And of course, when I say the 1970s, a lot of these things, they did take a while to settle down. I mean, ML is dated to 1972, but it didn't really sort of stabilize until the early 80s. Smalltalk didn't really stabilize until the early 80s. You know, the Lisp and so on in the early 80s. So it's not quite true to say they were stable by the 1970s, but they were definitely stable by the mid-1980s. So let's make, 1989 as our cutoff date, right? So here's the question, are you caught up with a state of art from 30 years ago? How familiar with are all these paradigms? And I would say most developers are probably not. We're not even caught up with the state of the art 30 years ago, most people are unfamiliar with, which is kind of sad. Now, I'm going to switch topics now. Let's talk about DIY. So if you're a DIY person and you like to do stuff around the house, you probably have a toolkit, and probably for hammering nails, you have a hammer. But when you want to screw things in, you use a hammer, right? And when you want to cut wood, you use a hammer. And when you want to tighten bolts or something, of course, you would use a hammer for that. Now, of course, this is not true. You wouldn't. You'd have different tools for different situations. No person would ever have hammers for everything. So let's look at your programming toolkit. For domain modeling, you use a hammer. For business rule, you use a hammer. For querying data, you use a hammer. For live coding, you use a hammer. Unfortunately, most of us use the same programming language for many, many different things. And I think a lot of that is because we're not even aware of other programming languages that can have a different way of doing things. It might be that another programming language is much, much better for doing certain things, but you don't even know it exists. So that's part of the point of this talk, is to improve, or at least get you aware of some other paradigms and maybe change, add some extra tools to your toolkit. So if you think about the popular programming languages right now, we have Java and JavaScript and all these things, right? They're all the same language. You might think that Python and Ruby and Visual Basic are different. No, they're different dialects, but the fundamental concepts that they are based on, which is imperative stuff with loops and mutable variables and stuff, they're all exactly the same. So we really do ourselves a disservice when we say we know quite a few languages, and we actually don't. We really only know one language with different dialects. So learning a new language from this pile, you don't get a galaxy brain if you learn C# and you already know Java. I'm sorry, they're basically the same language. I mean, if I was saying, I speak 3 languages, I'm a polyglot, I speak British English and I speak American English and I speak Australian English. It's like, I don't know 3 languages. I know 3 dialects, but I don't really know 3 languages. I can't speak, Chinese or a Native American language or an African language. Those are really different languages, and those are the kinds of things we should be learning as developers. So, it's a big world out there. There are lots and lots of different languages out there, lots of different paradigms out there, and we really should get away from the boring C and C# and Java and JavaScript world and explore, go out and try some different things. So let's go exploring. Let's start with SQL. So SQL was pronounced SQL originally, not SQL. And it was designed as part of a relational database, the world's first relational database. Now, before SQL, it was really terrible. Every database had its own proprietary API. So if you wanted to use a different database, you had to learn a whole new different API. I mean, can you imagine if you had to learn a different API for every single database you used? I mean, luckily, nowadays, when we learn Mongo and Redis and Cassandra and stuff, we don't have that problem. Isn't that nice? So yeah, SQL is a great step forward, and I think it's very underappreciated. So there's a couple of things we can learn from SQL as a programming language. We think of SQL as a lot of stuff, but it's a programming language first. And the first thing is that the model of the programming language is consistent. It's a very consistent model. Everything is relations. So a relation is just a set of tuples. You've got rows and columns. So, for example, if you say select the name from a table, that gives you a kind of subtable or a subset of the data. If you do a filter sideways, where you filter where the age is this, that gives you another subset of the data. And the thing about these rows and columns is that no matter what it is, it's always a table. It's always a set of relations, which means that you can, take a thing and filter it this way, and then you can filter it this way, and then you can join them together, and you always get the table back. And because it's consistent, you can make predictions. The nice thing about consistency is I can say, well, if it does this, I bet it does this too, because it's consistent. So if I say, well, if it's a set-based thing, I bet there's a way of doing Cartesian products. And you say, yes, of course there is. It's join. So you do a join, is a Cartesian product, and if you want to do an inner join, it's a Cartesian product with a filter. So that's the first thing. The second thing is that SQL is an expression-based language. I'm going to harp on about expression-based languages all through this talk. So what I mean by that is every thing in SQL spits out another thing. So if you take a query, the output of that query is, a table. But you can use that table inside another query. And you can take this query and use that inside another query. So you can embed subqueries into bigger queries, which means you can do this composition thing that I was going on about this morning. You can compose bigger and bigger queries from a bunch of small queries. Very powerful technique. So expressions are composable. That's one of the great things about expression-based languages. Just like Lego, you can build big things and small things. So that's great, and I'll have a whole talk about that. But there's another reason why expressions are great too, which has got nothing to do with composability, and that's to do with avoiding errors in your code and making your code more modular and making your code easier to understand. So if I switch to a kind of a C-like language like this, very simple thing, I have a result. If the Boolean is true, then I set the results and I print the result. So how many things can go wrong with this very simple code? Well, it turns out there's a lot of things. This result variable has to be initialized before being used. So what initial value should it be set to? Well, we assume the compiler is going to set it something, but we have no control over that. What happens if I forget to assign the result variable inside the if statement? Do I get a compiler warning? No. The compiler will say, oh, you got this result thing, it's fine, no problem. Because I don't have an else. So if it's true, I do this, but what happens if it isn't true? Well, I don't care. The compiler's not going to give you a warning. Shouldn't it give you a warning? So you forgot to handle this case? And then the final thing is that the side effects, if you think about assigning the value of result, that's basically, there's a kind of, not exactly a global variable, there's a variable outside of the scope which you're depending on. So it's kind of a side effect, which means you can't take this little statement and extract it out into its own method or its own function, because it depends on the result thing, which is outside of the scope. Now, if you have an expression-based version, which you can also do in C, If you say if it's a Boolean, it's either 42, and if it's false, it's 0. Now, what's interesting is the expression-based thing solves all that problems. You can't, the result thing is assigned at the end of the expression, not at the beginning. So you can't ever, you never have to say what's the default value. It's assigned exactly always when it's used. You can't forget to assign it. There's always an else case. You can't forget about the else case, and so on. And because it's no side effects, you can pull that little, obviously it's a little trivial expression, but you can pull this into a standalone sub-expression very easily. You can literally refactor it by pulling out and just pasting it in. So expressions are great for reducing bugs and for making refactoring easier. So expression-based languages are definitely the way of the future. In the 1970s, that was the way of the future. All right, what about SQL? Another thing we can learn from SQL is it's declarative, which means you say what you want to have happen, you don't say how to make it happen. So here is some C code I'm saying exactly what to do. I'm saying you need to do this and this and this and this. It's all very explicit. It's not at all obvious what this code does because it's buried in all the things about opening files and reading from the streams. Like, there's some logic in there somewhere, but it's not. I have to spend some time trying to figure it out. Now, if you look at the what version, the declarative thing, you say select everyone where the age is greater than 50. And I'm saying what I want to have happen. I'm not saying how to do it. I'm not saying that you have to open the file and you have to read these things and you have to like that. The SQL engine will do that for you. It will take care of that. You can focus on what's important. How to open a file and how to read it through it. That is not important. That's not important for this particular piece of trying to understand what the goal is. And because the query is independent of the actual implementation, it means you can optimize the performance independently of the code. So, for example, if I go to the C code and it's just too slow, and I need to put an index on the file, this code is going to change. It's really going to change a lot if I have to have indexes and stuff. But this code doesn't change at all. I just add an index to the table, but my actual business logic doesn't change. So you get decoupling, you get separation of concerns. And talking of separation of concerns, here's another thing. SQL is a query language. That's why it's called query language. It's a data query. Nowadays, we'd call it the data query language. And there's a separate language for doing updates and inserts. And there's a separate language for defining tables and stuff. Now, nowadays, all these are merged together into something we call SQL. But they were separate. I mean, they still are technically separate languages. The query language does not depend on the data manipulation language. These languages, they're separate things. They're not tightly coupled with each other. So what can we learn about SQL? Learn about design from SQL, learn to be predictable. Expression-based is great. Declarative interface is great. And separation of concerns. And also, it's interactive. You can play with it. You can type in a query and see what happens, and if you don't like it, you can change the query and run it again. You don't have to wait, half an hour while the code compiles. I mean, it sounds obvious, but if you were trying to do this in C or you're trying to do this in Fortran or something, you'd have to compile the code, and it would take at least a couple of minutes. I mean, maybe it'd take 30 seconds, but it's not going to be, literally interactive the same way. So what's interesting is even though SQL is over 40 years old, and it is expression-based, most modern languages are not expression-based. Sad. Right, Prolog, next up. So Prolog was the first mainstream logic programming language. It's French, and it stands for Programmation en Logique or something. Apologies for my French accent. Okay, the Americans are all into Lisp, and the Europeans were into Prolog for doing AI. And it was very big in Japan. Big in Japan it was. So, Prolog, just like SQL, was also very consistent. Everything is either a fact or a rule. So facts are kind of like rows in a SQL table. So here's a bunch of facts. Liz is 92, Charles is 69, Charles is the parent of Wills, and Charles is also the parent of Harry, and so on and so forth. So there's a bunch of facts. This is just the same kind of stuff you'd have in SQL. But in addition to that, you have rules. So a rule is a little thing that says, so-and-so is a grandparent of a child if the parent of a parent, and that is also the parent of a child. So there's Hopefully the code is clearer than my explanation. Or so-and-so is older than someone else. P1 is older than P2. If P1 has a certain age and P2 has a certain age, and age 1 is bigger than age 2. So these rules, now in SQL you'd have to do these with stored procedures or something, but in Prolog they're actually built into the language. And again, it's declarative. You don't tell Prolog what you want done. You say, you don't say how you want it done, you say what you want done. So, for example, I say, is Liz 92? And the answer is yes. Now, if I have an unbound variable, like which people are 92, it prints out all the answers. And it works the other way. I say, how old is Liz? So the A variable is unbound, and it says Liz is 92. And so it's bidirectional. I don't have to have two different kinds of facts. I don't have to query one way and then query another way. It's exactly the same code. So that's kind of nice. And if I say, is Liz the grandparent of Harry? The answer is yes. Is Will's older than Liz? Yes. Oh, false, rather. Who is Liz the grandparent of? And again, it's an unbound variable, and if I keep doing it over and over, it returns me all the different answers. So you can see it's almost like SQL, and in fact, a lot of people say, well, Prolog would make a really good query language as a sort of alternative to SQL. And in fact, there is exactly such a thing. It's called datalog. So datalog is to Prolog, what kind of the SQL version of Prolog. So let's say, I'll give you a little example. Let's say we have a kind of complex query. Get me the names and addresses of all the employees who work for at least one project located in Houston, but whose department is not based in Houston. So it's a really complicated thing, and even in SQL, you'd have to, be some sort of complex join of different tables and whatnot. So in datalog, this is how you'd write it. You'd say, we want someone who would, the nice thing about datalog is you make little kind of subqueries, quite nice. So someone who works on a Houston project is somebody who works on a project, and that project is based in Houston. Someone who doesn't live in Houston is an employee for a department, and that department is not based in Houston. And then we say the answer is we want the first and the middle and the last name and the address of an employee who has a manager, and the manager works in Houston but doesn't live in Houston. So, it's quite a complicated query, but you can actually break it down into little pieces. It's quite a nice, quick kind of query by example model. This bidirectional unification kind of thing that Prolog has is pretty awesome. I mean, there's a thing in Prolog called append, which concatenates two lists. So you have I think it does concatenate two lists, yeah. So if you concatenate 1 and 2 and 2 and 3, you get the list 1, 2, 3. So if you say what is the list that you get when you add 1 and 2 and 3, it gives you the answer. So there's only one answer. But you can put the kind of missing variable anywhere, because it works in all directions. So if you say, what do I have to add to 2 and 3 to make 1, 2, 3? And it's saying, you add 1, okay? And then what happens if you put multiple kind of unbound variables, okay? Well, there's multiple answers now. Well, x could be empty, and y could be 1, 2, 3, or x could be 1, and y could be 2 and 3, or x can be 1, 2, and y can be 3, or x can be 1, 2, 3, and y could be empty. So there's 4 different possible answers, and it will find all 4 different answers for you. Because so this is a very cool thing, I think. So let's do a Prolog demo. And where is it? Here we go. Right, so here is some demo code. And I'll just make it. So here's the thing I was talking about. If I say, here's the parent of Harry, it's Diana and Charles. You see, it'll give me all the different answers. And if I say, is Liz the parent of Harry? I'll say no. Is Diana the parent of Harry? It'll say true. So, that's all it is. It's pretty simple, but it's interactive. You can do cool stuff with it. Let me show you a more cooler thing, which is Sudoku. And I'll just make that one. So, hopefully we all know how to play Sudoku. Now, if you're trying to write a Sudoku solver in C# or Java, you'd probably spend a lot of time on the algorithm of how to actually solve the problem. In Prolog, you don't. In Prolog, you set up the rules, you set up the constraints, and it figures it out. This is the thing. If you say, you don't say how to solve, you don't say what you want to do to solve the problem, you just say, this is what the problem actually is. Here are the constraints. Can you find something that matches these constraints? So I don't know, hopefully you can read this okay. So we say Sudoku means there's 9 rows, and the second one says each row has the same length. And that each row has the values in each row must come from the set of numbers from 1 to 9. And all the rows are distinct. And if you transpose the rows, you get something called columns, and all the values in the columns must be distinct as well. And if you break the rows up into blocks, which is, the 9 different blocks we have, we also say that each block must be distinct. So that's it. That's the entire Prolog program for solving Sudoku. Now, we actually haven't written any kind of code. All we've said is these are all the constraints for, this is the rules of Sudoku. It's not actually the algorithm. But then if we go and we say, here's a problem, and what we're saying is all the underscores are things we don't know the answer to, and we've got a couple of numbers in here. We know this is a 3, we know this is an 8. And if I go over here and I say, please solve this problem, and it says, oops, did I not? Try again. There you go. So it's actually managed to fill in all the gaps for that game, because the constraints uniquely define how Sudoku works. Now, if I go to another version, this one here, I've made a bad one. I put 2 8s in the same row. Okay, so this is an unsolvable Sudoku. So if I go to Prolog and I say, please try and solve all the constraints for this one, for problem number 2, it will say false. It cannot find any things that match. So it's pretty cool. So obviously, Sudoku is sort of a toy problem, but there are many situations in business where, you have rules like you find the lowest price. If this thing complies, you have to deliver this thing on this day and this thing on this day. What's the best way to have the trucks drive around to do it? Constraint solving problems is a really, really common thing in a business, and Prolog is really perfect for doing that. It's the whole way that Prolog works. So what can we learn from Prolog? It's consistent, it's predictable, it's declarative again, its unification is awesome. It seems like magic when you see how it works. Really very cool. And it's bidirectional, which is cool. And it's interactive. Again, I didn't have to compile stuff. I could literally run it on my own computer. So, I've seen businesses spend a lot of time working on rules engines and special kind of algorithms to solve these kinds of problems. Like, no, just use Prolog. Prolog is what does it for you. And you can, most of the Prologs have an API. You can call it from Java or whatever. It's like, you shouldn't basically reinvent the wheel. If you have this kind of problem, use a tool that does it natively. Right, next is ML. So ML stands for meta language, not to be confused with machine learning, and it was designed as part of a theorem proving system. So it's an academic kind of language. It's an impure functional language. It's the parent language for standard ML and OCaml and F#. A whole generation of languages are very ML influenced. There's another branch, the kind of Haskell branch, which is pure functional languages. They came from a language called Miranda in the early 80s. So I'm not going to talk about functional programming. You've probably heard enough about functional programming. But I am going to talk about things we can learn from the ML family of languages, which are still useful today, without talking about functional programming. So the first thing that ML languages have is type inference. And this is the same kind of algorithm that Prolog has when it does unification. And let me show you what I mean. Here is a function. And by the way, I'm going to be using F# because the ML from 1972 is kind of hard to get hold of. And it's really not that particular thing. It's the ML influence languages that I'm going to be talking about, and F# is one of those. So this is how you define a function F#. It's got 2 parameters, f and x. And we say y is f of x plus 1. And then hello plus y. Now, we haven't said anything about what f and x actually are. So can the compiler figure out what's going on? Can it figure out what these types are? And the answer is yes, it can, because what it does is it says, well, you're adding 1 to something, so x must be an int, right? Because you're adding 1 to it, so x must be an int. Similarly, if you're adding y to hello, y must be a string. So y is a string and x is an int. Now f is a function, because we're passing in a parameter, and the input of this function is an integer, and the output of this function is a string. So f must be an int to string function. So there we go. We've solved this particular piece of type inference here. F is an int to string, x is an int, and the overall return value, which is hello plus y, must also be a string. So this is the kind of thing you've got. The nice thing about this is you get code that looks like a scripting language. It looks like Python or something, but it's actually statically typed. And if you make a mistake, the compiler will tell you. So to me, this is the best of both worlds. I think type inference is awesome. Right, so that's thing 1. Here's a more complex example. This is C# code. This is a method in the link library, group by, which the return value is an I-enumerable of an I grouping of a T key and a T source, and it takes an I-enumerable as input, and it takes a func of a T source and T key. Like, I challenge you to try and figure out what this is. What are all these things? What are all these types for? Could put it this way: if I told you this, could you figure out what the type signature was yourself? If I hadn't told you, probably not. Now the F# code, the equivalent F# code, looks like this. There are no types in the signature. So the nice thing about type inference is it's less typing. You don't have to type the type. You don't have to type everything over and over. So it's less typing. But the other thing is it's less noise. When I look at the F# code, I can focus on the logic. The fact that there's all these types, the C# code has so much stuff floating around, it's a lot of noise in my brain that stops me actually trying to look at what's really trying to go on here. So I think that's a really important thing. No noise, less noise is good. And this is a great quote I found on Hacker News. Type systems and Prolog have a lot in common, and people who write their own type systems are basically re-implementing Prolog. So there you go, use Prolog if you're implementing a type system. Right, number 2, different defaults ML languages have. In ML languages, things are immutable by default. If you want mutability, you have to ask for it. Things are non-null by default. If you want nullability, you have to ask for it. You get structural equality by default. So 2 things have the same data, 2 structures have the same data, they're equal. You don't have to override equals and get hash code and all that stuff. You get that for free. Now, if you want reference equality, you can get it, but you have to ask for it. It's not the default. And everything has to be initialized. Right? You can't have classes where some of the data's there and some of it's not. So those are really interesting defaults, just from a kind of sanity point of view. I mean, they may not be that big in the scheme of things, but in order to reduce bugs, I think it's actually really, really useful. These are very, very sensible defaults. Okay, algebraic type system is one of my favorite topics, and I like to call it a composable type system rather than an algebraic type system. And that's only possible because the types in a functional programming language don't have behavior. In an OO language, behavior and types are mixed up. In functional languages, they aren't. So, by the way, this is technically, the original ML technically didn't have this, but standard ML has it, and most ML languages have this now, so I'm going to call this an ML feature. So, in a composable type system, you build bigger types and smaller types in 2 different ways. You either AND them together or you OR them together. So when you AND things together, like fruit salad is an apple and a banana and a cherry, say, this is something you're familiar with. This is what we call a record type or a struct or a tuple or something. Very, very common, nothing surprising there. But when you OR things together, this is something which is kind of unique to algebraic type systems. You can choose. You can say it's an apple or it's a banana or it's a cherry. So this is a choice type. I like to call these a choice type. And you write this with a vertical bar in F#. So these are really, really useful types. It's useful concepts because you can build really big, complex types from these building blocks. So here's an example of how you might do this for a payment system. Let's say you accept cash, check, or card as your payment. And for cash, we don't need any extra information. For checks, we need a check number. For credit cards, we need a card type or something. So how would you implement this? So in an OO language, you might start off with some base interface and you might implement various subclasses. With an algebraic type system, you build it up from smaller pieces with composition. So you start off with some small pieces like this, which are primitive types, and then you might say, well, a card type's a choice between a Visa and a MasterCard, and then credit card information it's a card type and it's a card number, so that's a record type, so a choice and a record, and then we build on top of those, and we say a payment method is a choice between cash and check, and if it's a check, you've got a check number, and the other choice is a credit card, and if it's a credit card, you've got some credit card information, so that's a choice type. And then you can keep going, keep building and building and building. You can say, well, payment amounts, that's a primitive, currency is a choice between euros and dollars, and keep going and going. So payment is all these things, it's an amount, and it's a currency, and it has a method, say. So you can, like a one page of code, you can actually build up really quite a complex domain model. So I think this is great. And what's cool about this is executable documentation, one of the goals of the Agile movement. So if I show you all these types, I think you can guess what's going on here, even if you don't even know F#. I mean, this is very, pretty self-documenting code. It's pretty clear what's going on. Even if you're a non-programmer, you could probably figure out most of this stuff. So these are the nouns, and you can also have verbs by making functions have types as well. So this says, to pick up a card, you have a hand, you have your own hand, you have a card on the table, that's the input, and the output is a new hand. So you can do very expressive stuff. The entire domain fits on one screen. And again, if you show this to someone who's not an expert, and you say, can you guess what payment methods are accepted? I think people could. You don't have to look in 4 different files and look in the subclasses and find out which subclasses have been implemented. It's in 4 lines of code right in front of your face. So this is a great idea, I think. It's a massive topic. I have a whole talk about DDD. I have a whole book about it. So if you're interested in learning, you can watch my talk. Right, I'm not going to do a demo of ML because you've seen enough F# and stuff this conference, so I don't think you need to see more. What can we learn from ML? Hey, it's an expression-based language. What a coincidence. So we've seen 3 expression-based languages already. Type inference is awesome. What it does is especially it allows you to work very quickly. You can add and remove parameters very quickly without trying to figure out what's going on. And it makes bad things harder to do. By having these things like things being immutable by default, it just prevents you from doing stupid stuff, I think having the defaults are really important. If you have the defaults that make it easy for you to do stupid stuff, you're going to do stupid stuff because you're lazy or you forget or whatever. If you can't do stupid stuff by accident, then you're just less likely to have mistakes. So I think that having proper defaults is important. If you guys ever design an API or something, make sure your defaults are good. ML was the first language, as far as I know, that had parametric polymorphism, that we call generics. And of course, it had algebraic types, which are awesome. Right. So the type inference stuff, by the way, the Java has just got var. So they just got a feature that was around 40 years ago, and they're still kind of worried about it. And certain languages don't even have generics. So certain brand new languages that do not have generics mentioning no names. And once you get used to algebraic types, they are so amazing for domain modeling, you can't live in a language that doesn't have them. So it's really hard to express how good they are. All right, now time for Smalltalk. So which went through various variants. 1980 was the major one, but I'm going to include the 1976 one because I want to include it in the 1970s. So I heart Smalltalk very much. It was my first love as a programming language. I spent a big chunk of my life working on Smalltalk, and I still love it very much, and I highly recommend that you love it too. When Smalltalk came around, a lot of people thought this was a great way to interact with a computer. This is a teletype. And, is a teletype, luckily, no one thinks that teletypes are the best way to interact with computers now, do they? No? Do you think that a TTY interface is related to this? For some reason, a lot of people think that TTYs are still the best way. We don't have a physical thing like this, we have a console. But even so, we're typing stuff in, right? And it's 40 years later, and we're still typing stuff in. So Smalltalk was the idea that computers should be interactive, and they shouldn't be ugly, text. It should be a whole interactive experience. It was developed at Xerox, and Xerox PARC did amazing things. They did the first PC, the first GUI, the first laser printer, the Ethernet, all sorts of stuff was developed there. Just incredible. Smalltalk introduced a lot of features that we take for granted now, a message-based OO, model view controller, a windowing IDE, a virtual machine, generational garbage collector, etc., like I say, many, many galaxy brains. This is the Smalltalk user interface from 30 years ago on the Mac. Hasn't really changed that much. You can see it's really interactive. Obviously, the bitmap was pretty low res, but we still use this kind of interactive IDE today. So, first thing to learn about Smalltalk is it's got a consistent model, which that everything is an object. And when it says everything object, it really means everything is an object. Everything is an object. Can't stress this highly enough. The compiler is an object, the stacks, frames are objects, the debugger is an object, the windows are objects, integers are objects, bits are objects, everything's an object. The other thing about Smalltalk, which is very interesting, is it has a very minimal syntax. It has 3 keywords, and it has only 3 ways of doing it. I mean, they say it fits on a postcard. That's how small it is. And what's interesting about that is if you have a minimal syntax, you're forced to put power into the language. When you want to do new stuff, you want to make the language powerful enough that you can do new stuff in the language without having to change the compiler. And this is also part of the Lisp philosophy too. If you want to do something in Lisp, you want to implement objects in Lisp, you implement it right in the Lisp system. You don't need to change the Lisp language. An interesting example of this happened just recently with F# versus C#. They both introduced async. In F#, they didn't have to change the compiler because async is a library. In C#, they had to change the compiler because async is a compiler keyword. So, and they also did it for performance reasons. So, I mean, I understand, but there's a difference in the expressivity of the language, or the philosophy behind the language of how do you add new features? Do you change the compiler? Do you add new keywords? Or do you make the language so powerful that it can basically do anything without ever changing it? Smalltalk also has late binding. So late binding means that nothing really happens until the very last second. So if I send a message to an object to do something, I can intercept that message at any point and play with it and tweak it and do stuff, and we'll see an example of that. So if you're going to be a dynamic language, be really, really dynamic. I mean, literally so dynamic that you can change anything at one time. And finally, Smalltalk doesn't have text files. Who needs text files? Everything in Smalltalk is in memory. All the entire classes, all the engines, all the compiler, everything's in memory all the time. And that means everything's accessible and you have a lot of power. And it means you don't have to worry about where your text files are stored. And you might think, well, that takes up a lot of memory. Well, when I was using Smalltalk in the 90s, it used about 2 megabytes. 2 megabytes of memory, it's pretty shocking. I think a Google Chrome, how much is a Google Chrome tab? Nowadays, like 50 gigabytes or something. And I'm just saying, we're worried that it's going to take up too much memory. No, compared with other stuff we do, it's trivial. Now, let's do the wonderful Smalltalk demo. So I can get rid of this. Oops, where are we? Here we go. So here's number 42. And there's different messages you can do with 42. You can do what you call a binary message. And you can do a unary message, which doesn't have any parameters. And you can do a keyword message where you have to pass in the parameters. So every time you see a colon like this in Smalltalk, that's a thing with a parameter. Now what's interesting is when you run this code, it puts the answer right in the thing. The idea is meant to be interactive. So I could then immediately start working with it. What's the length? Does it have length? No, I can't remember what it is. Anyway, you can start playing with all the different things, on the command line. Right. Obviously, you have to be very careful when you put in very large numbers, because if you do something like this, what happens is nothing happens. You get the very large number back. Smalltalk is designed not to break. It's designed to hide the implementation from you. As a user, why do I care about overflow? Do I care about 32-bit ints versus 64-bit? No. Why do I care about that? So why force me to care? I should be able to do, very large numbers. 100 factorial should be fine. Right? Try doing that. And it takes it. It goes all the way down to something like, what is 1/2 plus 1/3? What's the answer? 5/6, obviously. So things like fractions, large numbers, all this stuff is built in because you shouldn't have to think. You shouldn't have to say, oh, I wonder why it's doing that. I wonder if it's overflowed. It's like, no, that's never going to happen. It hides all that stuff from you. The whole point is it's meant to, your mental model is meant to be more important than the computer model. Okay, now let's look at this late binding thing. If I say 42, hello, whoops, not hello. It says, small integer does not understand hello. Now, what am I supposed to do here? Am I supposed to stop and fix the bug? No, I'm actually going to go right into the debugger, and I'm going to go to the error message, and I'm going to implement the method right here. And I'm going to say, hello from NDC. So I'm in the debugger. I've changed some code. Now, if I keep going, there you go, it works. So I basically intercepted a message, wrote some code, and carried on programming. And this is actually really common in Smalltalk. You actually write a lot of the code in the debugger. You basically write the code. It's almost like kind of TDD. You write some code, none of it works, but in the debugger you write all the methods until it does work. And by the way, which file? I just wrote a new method. Which file did I put the method in? Did I have to? I didn't have to think about where it went. Right? One of the nice things about not being a text-based system is that it's just the whole load off your mind. If I was going to do this in C#, yeah, I could probably fix things in the debugger, but then I have to decide where am I going to put the method, which files are going to live in, There's a lot of stuff I have to think. It interferes with the programming. This is just overhead. It's accounting. I don't want to think about that when I'm programming. I just want to be able to type stuff and have it work. So Smalltalk is perfect for that. Now, I said that everything is an object, so 42, of course, is an object, and because it's an object, it has a class, which is small integer. Now, small integer is also an object. So I can say, what class are you, small integer? And it says, I'm small integer class. Oh, thank you very much. Now, in Smalltalk, there's no such thing as instance methods and class methods. Static methods and instance methods. Everything is an instance method for somebody. So the class methods are actually, there's a pair of classes, the kind of main class which has methods, but the class methods or the static methods are actually instance methods of another class. And the class methods of that thing are actually instance methods of another class. So you can go all the way up the class hierarchy. Small integer class is of type metaclass. What class are you, metaclass? Metaclass class. What class is metaclass class? Actually, at this point, you get a loop. It goes back to being a metaclass. But the point is that everything is an object. And I can do stuff like, say, open up a browser on 42, and it takes me straight to the place in the class hierarchy. 42 is a small integer, which is a subclass of integer, which is a subclass of number, and so on and so forth, all the way up. And I can see all the different methods that are available to me for integers. So this is an interactive IDE, just like you're used to. This has been, like I say, this has been around for at least 40 years. And it's still probably one of the best IDEs out there. Okay, let's talk about creating classes. So if I was a OO person, you think I'd be in most OO languages, they have a special new keyword. So if I want to create a new animal, I would do something like this. Smalltalk doesn't have a new keyword. Doesn't have any keywords hardly. The way you create a new animal is you send a message. So you go to the animal class, and you say, I want to create a new animal, and I'm going to call it, say, a cat. And there it is, it's a cat. And if I browse it, there it is. You can see it's in the animal class and so on. So everything is a message. You create classes by sending messages. You create instances by sending messages. You do everything by sending messages. Like I say, everything's an object. Now, if I want to create a new class, that was creating a new instance. How do I create a new class? Well, the answer is I send something a message. So this is a message. It's actually a message with 5 parameters. So if I want to create an animal2 class, I do it by sending a message to somebody. I send a message to the object class, and I say, I want a subclass called animal2. And I don't need this, and it's going to have maybe a name and an age inside. There it is. And there it immediately shows up in the class browser. So everything is sending messages. Right, what else have I heard? Oh, yeah. And of course, which file did I put this new class in? I don't care. It's not relevant. It's just stuff that gets in the way. Now, I talked about not having keywords. I mean, not having a very simple syntax. So something like if true, if false. In Smalltalk, there's no if statement. How do I do ifs in Smalltalk? I use messages. So I say 1. If I say 1 equals 1, if true, what am I going to do? I'm going to say yes. And if it's false, I'm going to say no. And that's yes. And if it really isn't true, for some reason, I'm going to say no. So this if true, if false is a message that I'm sending to a Boolean. All right, like I say, there's no special syntax for if true or if false. There's no special syntax for looping. There's no special syntax for switch statements or for, I don't know, think of all the syntax you have in your favorite language. How many keywords there are in C or C# or something. None of those keywords exist in Smalltalk. Let's look at the implementation. Since it's a method, we can look at it and we can also change it if we want to. If we want to be stupid enough to change if true, that would not be very sensible. There's 3 different implementations of if true or false. One is at the Boolean, which is the parent, and there's 2 subclasses, one called true, one called false. These are very small subclasses because they have slightly different behavior. Now, the Boolean definition of the method says, not my problem. It says subclass responsibility, right? So if I try and call it, I'm going to get an error message. Now, if I look at the definition for the true subclass, it's going to say true. It's going to take the true block, which is, you can think of it as like a lambda. It's going to take this block, and it will just run this block. Now, the false implementation is exactly the opposite. Oops. The false implementation takes the false block and runs it. So if you know anything about lambda calculus, this is how if true and if false is implemented in lambda calculus. So it's quite influential on Smalltalk. Anyway, that's enough about Smalltalk because we're running out of time. So I just wanted to show you that Smalltalk is really cool. What can we learn? It's got a consistent model. Minimize the syntax and make the language more powerful. Be awesome and make people fall in love with you. And that's not a joke. A lot of the stuff in the 80s, the Apple Mac, they really wanted people to love it. It wasn't just a piece of hardware. The Smalltalk, people who designed Smalltalk really wanted you to fall in love with it. They put a lot of effort into the icons and the language and the interactivity of it. So if you're designing a program, think about making people fall in love with you. It's a really good thing. It will really make your program much better. Okay, so I'm just going to be about 5 minutes over. I hope that's okay. Just finish up with my mysterious language X. So a lot of people say, well, it's Smalltalk self-contained. It doesn't use a file system. It's interactive. It's got surely it's a dead end. People don't do that kind of stuff anymore. So language X. Let's look at language X. In the 1980s, people would pay thousands of dollars just to use this language. That's how important it was. Its descendants have been at the heart of software products which dominate their field. And its grandchild is probably the most popular program language in the world. Who knows what I'm talking about? I bet some people do. So yeah, the answer is VisiCalc. So VisiCalc came out in 1979 and immediately became incredibly important. And of course, VisiCalc begat Lotus 123, which is the most important language of the 80s. And that begat Excel, which is still one of the most important programming environments. Now, what's interesting about Excel and VisiCalc and so on, it's a programming environment, right? It's something where you type in equations and you get the results interactively. If you couldn't type in formulas in Excel, it wouldn't be popular. So anyone who uses Excel is programming. And that's why it's the most popular programming language. It's actually a functional programming language. So why was VisiCalc so important and so successful? Well, it's got a consistent model. Everything is a cell and a formula that acts on the cell. Okay? It's super, super interactive. The whole point, if you had to compile your formulas in Excel and wait 30 minutes before you could see the answer, it would be a complete flop. The fact that it's super interactive, you type something in, it shows up over here. That's one of the reasons why it's so great. So it's an interactive environment and a programming language. It's hard to say, is it a programming language? Well, it wouldn't exist without the interactive environment, but the interactive environment would be useless without the programming language. They fit together kind of, it's one integrated system. You can't separate them out. Now, just like SQL, it's a domain-specific language. It's an expression-based language. It's a language that non-programmers can use. Like A1 plus B1 divided by 2, that's the kind of thing you could put in a formula. And it's functions. It uses functions everywhere. So when you do sum in Excel, you're doing functional programming. And like Prolog, you program sort of by filling in slots. You fill in all the cells, and it figures out what's going on. And of course, like Smalltalk, there's no separate text files. When you save a formula in Excel, you don't say, I want to save this formula in this file. No, you save it in the entire environment. You save the entire Excel environment. You don't save a particular formula to a particular file. So what can we learn from VisiCalc? Well, programming appears in many guises. We think that programming is running things through a C compiler or whatever, typing in Vim. It's like there's a lot more to programming than that. It's making a computer do what you want. So programming is not just for programmers. I mean, it's a shame that it should just be for professional programmers. People love to interact with their environment. They want to explore stuff. And programming for a particular domain is actually a lot easier in general than general purpose programming. If Excel used like a C language instead of the Excel macros, whatever, again, it would be a complete flop. So we tend to be thinking about that everyone's just like us, and we're all into like hardcore programming. There's a lot of Excel programs out there. There's a lot of people who program in other systems. People used to do a lot of Flash programming. People do CSS. CSS is a programming language. All sorts of stuff, And use the right tool for the job. Don't use Fortran in an Excel program. It's not the right tool for programming a spreadsheet. Fortran is great for some things, but it's not great for other things. Prolog is great for some things, but it's not great for others. Use the right tool for the job. Okay? Don't always use a hammer. So, there are lots of different approaches out there. Get yourself a bigger toolbox. And C-style syntax is not the only syntax. All these languages I've been talking about, none of them had a C-style syntax. Even Smalltalk didn't have dots. There was no dotting into something in Smalltalk. Right? It uses spaces. And when you end a sentence, you use a period or full stop. You don't use a semicolon. It's not proper English to end sentences with semicolons, okay? So you notice that Prolog and Smalltalk use full stops to end their statements or their expressions. No curly braces anyway. You haven't seen a single curly brace today. No dots in. Okay, so a language that doesn't affect the way you think about programming is not worth knowing. So please go and expand your galaxy brain, go and learn some new languages, go and change the way you think about stuff, and it'll be great for you. So off you go. Thanks very much. This slides and video will be up on my website, and if you like my book, you can read all about it there. So thank you very much.